E equals mc² is possibly the most well-known equation in the world. Most people know that it means that mass and energy are equivalent, by a very large factor. If all of the 4 kilogram mass in a baby was converted into energy, by annihilating it with a 4 kilogram anti-baby, it would release 719 petajoules, about 11,400 Hiroshima bombs worth of energy. The speed of light squared is a very large number, but why is E equal to mc²? And how does this fit in with the rest of special relativity? One of the assumptions we need to derive Einstein's equation is that of relativistic mass. The mass of an object increases as it approaches the speed of light. This is itself derived from the law of time dilation, so if you haven't watched part 1, go and see it now. Now, imagine another train travelling at near the speed of light through a station. Remember that the train gets shorter in the direction that it's moving and has slower time. A person on the platform throws out a red ball at velocity v towards the train, and someone on the train throws a blue ball in the opposite direction. The two balls collide perfectly elastically in midair, meaning that the red ball bounces back towards the platform with velocity minus v. However, the time for the blue ball is slowed down as it is moving so quickly along the track, and there is negligible length contraction perpendicular to the direction of motion, so its speed in this direction must be less than v, as seen from the platform. Let's just say it's 3/4 as much. In the collision, momentum, which is equal to mass times velocity, must be conserved, and the only way this can happen is if the mass of the blue ball is greater than the mass of the red ball. If I display the masses of the balls, you'll see the blue ball weighs 4/3 as much as the red one, in this case. Looking at this from the frame of reference of the train, the same happens, except the mass of the red ball is now larger. This is where the bane of sci-fi accuracy comes from. As you approach the speed of light, your mass increases, and so the force required to accelerate you also increases. At sea, your relativistic mass is now infinite, and so you cannot be accelerated further. Faster than light travel is therefore impossible, unless you use certain tricks, for example the Alcubierre warp drive, wormholes, or quantum teleportation, all of which may be the subject for a future applications video, once I get the fundamentals down. However, all we need to know for this derivation is that nothing's velocity can be greater than c. Now, we can see how energy can be converted into mass. Imagine a spaceship travelling infinitely close to the speed of light. For 1 second, a force is applied to the spaceship. Thanks to Newton's second law, a force applied for a certain time produces a change in momentum. Since the ship cannot go any faster, that change in momentum must be due to an increase in relativistic mass, rather than velocity, which stays at c. Let's say the ship's mass increases by amount m. The change in momentum is therefore mc, which is produced by a force of magnitude mc acting for 1 second. The distance travelled in this time equals speed times time, so it travels c meters when the force is acting on it. The energy gained by something is defined as the force applied multiplied by the distance travelled. Therefore the energy, E, equals force, mc, times distance, c, which gives us E equals mc². Now, this derivation only applies in this specific case, and it requires very complicated mathematics to prove this to be true for all situations and for all types of energy, but it can be done. Einstein showed that energy and mass were facets of the same thing, mass energy, which is always conserved in any interaction. His formulas had many applications, for example nuclear power, which is so efficient because some of the mass of the nuclei is turned into large amounts of energy. And with that, I think I've covered most of the basics of special relativity in these 2 videos, but let me know in the Reddit if I've left anything out. Thanks for watching, and I hope to see you soon for some more fundamental science.